Hello, I'm David Hunter, and I'm going to explain to you how to use the hyperbola detection system within GPR-SLICE. Now, this is a particular module that's only available in the bridge deck module, which you'll need to. It's an optional extension of GPR-SLICE, so this isn't available to all users by default. You'll need to pay an extra fee for this particular feature. So we've done all our data processing. Crucially, you need to make sure that you've done your bandpass filtering and you've done background subtraction filtering for this to work. If you haven't done those two, then what happens is that the amplitudes of the hyperbolas in the radargram will be influenced by this for instance, by horizons or by frequency noise. So what we're going to do is we've done our bandpassing and we've done our background subtraction filtering. So we're going to choose the filter option, the filter folder to operate on. So simply click on the search button, and we're presented with a series of options at the top here. Now, the idea is that you want to fit a curve to a reflector, and there's a series of dots that will display, and you need to get those dots exactly in the right spot. If you don't do that, then, well, if you don't get it in an ideal spot, the detection system won't work properly. So this is a fairly fiddly system to get working. It's best used for concrete scanning work, where you're looking for reinforcing bar in concrete, which is relatively homogeneous. You're not going to have all of these strange layering that you normally get in a soil profile, for instance. So unfortunately, the concrete data that I have isn't a very good example, so we're going to be running with the worst case possible data set that you can possibly have, which is from a rock garden. So let's say this reflector here is fairly clean. So we'll use that as an example. So I'm going to change the X and the Y pixel values at the top here just to enhance the display a bit. And let's bring that to, say, 500. And then click on resize. Now we want to show, because we want to concentrate on this particular reflector, we can change the range start and end values. So the range is defined by the x-axis, of course. So if we wanted to, we could just display 0 to, say, 30 meters along the range. So do that, and then click on the scroll button, and then we'll just crop the image just to that particular section of the radargram. Okay, so here's a fairly clean reflector, and there's also another one here that might be a good target. So what we need to do is, first of all, we need to bring up those dots that I mentioned earlier. Now you've got an option of either using 3 dots or 5 dots, and the benefits of each will become apparent in a moment. But what I'll just show you first is some screenshots of this is what we're looking at. This is what will come up when we click on the button. You'll see that there's a series of 5 dots, 5 yellow dots. Now, when we click on the Help 3-point horizon button, we're only using these 3 dots, these inner 3 dots, the center and the 2 inner dots. However, if we clicked on the Help 5-point horizon button, horizontal button, then we're going to use all 5 for this process. There is an alternative option, which is vertical, and instead of aligning these horizontally, then you'll see them vertically, and you'll just have to experiment with which option works best for your particular data set. Now the goal of this is to get these, or this black, or this center dot needs to be at the top of the reflector, so where I've put it now essentially. The outermost, or the innermost of the two, these 2 points here, these ones here, need to be, in this case our center one is on a black is on the black section of the reflector. So these ones need to be put on the white section, just outside of that. And that's for the 3-point. If you're using the 5-point, then you also have to put these ones, these outermost ones, onto the black section that's beyond the white section. So what your ideal would be is something like this. Although that's not exactly correct, as you can see, because we've got some layering going on here. There's actually some dimming of the white section of the hyperbola. So this is where it becomes incredibly important to get clean radargrams to begin with. So we're going to have a bit of difficulty with this particular data set. If you've got a concrete data set though, where there is no background noise, there aren't any issues, then you might not. Then in theory, you shouldn't have this problem. But okay, so let's start off with this particular one. Now we know that the reflector starts at, well, we can see in the upper left in this section here, there's a sample number, and at the moment it says 3. As I move across it, now it says 15, 14. So that reflector starts at roughly 17 samples down the radar trace, and it ends at roughly 51. So what I've done is I've put here N1 and N2 of 10 to 60. So that covers that range of values when we know that the hyperbola is. N-skip is a number that says if it detects a reflector at say 17 samples, it will then ignore any reflector between 17 or between 18 and 28 samples. So directly below that reflector. So this is useful for instance, like this one here, where we've got multiple reflections coming off the same object. It will ignore that. So you want to change that based on, if you're getting too many reflectors detected on the one actual hyperbola, then that's the value you need to change. N nearby, however, does the same thing but in the horizontal axis. So if you find that, for instance, here you're getting looks like there might be a small reflector here. There's this one here. There's that one there. If you want to only get this one, for instance, then you can change that to that value. And that's particularly useful for if you've got a lot of small rocks or things like that in the ground, where there are multiple hyperbolic reflectors overlaid on top of each other. Okay, so let's get on with it. If we click on the Help 3-point horizontal mode, up come our 5 dots. Now our goal is to put the center dot on that black section in the center. The two either side of that center point need to be within the white section, so we're almost there. At the moment it's just off a little bit. And the outermost ones need to be within the black section outside of the white section. So we just need to narrow this a bit, and by default the migrator window is set to this part of the scroll bar. Unfortunately, that doesn't actually relate to where the red lines currently are on the radargram, so we'll have to experiment a bit with this. See, if I change that back, it goes to that wide, so we need to narrow that down a lot. Almost there. Make it narrower. Close. Okay, now we've gone too far. A little bit more. There we are. It looks like it's a bit too wide on the outermost ones, but we'll give it a try. So just left click, and you'll see in the upper section there's a series of numbers A1, A2, A3, and that relates to, if I go back to my screenshot, this value, this dot here is called A1, this one A2, and that one A3. Now, if you're doing the help 5 point, then it would be different. This one would be A1, A2, A3, A4, A5. But in this case, we're only using we're only using 3, so values A4 and 5 won't change if we're using the 3-point value. Okay, so that's given the system a series of amplitudes to use as a calibration for detecting a hyperbola. So if we click on auto search, there we go, it's picked up quite a few. Now, as you can see, there are some false positive, and it actually has completely missed this reflector, and it's missed this one as well. Now, why is that? Well, that's because we've used an ideal, relatively clean reflector as our calibration. So that means that it's not going to detect these fainter ones at all. And sometimes, as you can see, it gets it completely wrong. This is why this system is really only is designed for use on concrete, where you're looking for reinforcing bars, or rebar, where there is no, or 99% of the time in concrete, there is no layering like this, and it's relatively homogeneous. You're only going to get the reflectors within the concrete block. You're not going to get all this other extra noise. So unfortunately, I don't have a good example of this, but that's how you do it anyway. That's how the system works. Okay, so if we go back and click on the resize button again, that will reset the scrolling values that we had. And now if we click on auto search again, it's now showing all the ones that we've detected throughout the radargram based on that particular hyperbola that we used as our calibration. So that's how you use the automatic hyperbola detection system. And if you want to, you can close out of here and click on compile hyperbola amplitude, and it will create hype1.dat. To the right hand side here of our uppermost area, these A1 values, A2, A3, the A stands for amplitude, and it's essentially a measure of the millivoltage of the signal received by the radar system when the signal returns back from that particular reflector. So what this means is we can create a grid for depth slicing if we wanted to, only on using only the radar scans or radar traces that fall within these detected hyperbolas. So we can completely ignore all of this data, all of that data, all of this data, for instance, if you wanted to, and only take the radar traces between these and then create a depth slice out of that. And the reason for that is, and in this case, obviously, I don't have rebar, so it's not a good example, but if you were doing this with rebar, you could just create a depth slice of the amplitudes of all the reflectors from each rebar, and it would essentially, it would give you a map showing that some area where different areas might have a different amplitude reflector. And the reason for that would be, for instance, if your reinforcing bar is corroding in a particular area, then it might not be capable of reflecting the radar signal as well or to a greater amplitude as some other areas. So it's a very quick way of creating essentially a map of the reinforcing bar deteriorating. So all we have to do, click on the compile hyperbola amplitude button. Okay, and obviously this isn't going to be a very good example, but it'll give you some idea as to how to actually go about doing it. So we've now created hype1.dat. Close that up here. Close this. Go to our grid menu. In the input directory, we're going to choose our hype option. And then click on gridding. And of course, there's only one file, so you're going to get this hype2.dat error, which is fine because you're only getting one anyway. So as you can recall, there was a gap at the start of our radargram where there was nothing detected, so it's deleted that from the depth slice, and there's a section here, and so on. There's gaps in between each individual reflector in our depth slice, or it's not a depth slice anymore, it's a map of the amplitude solely for the detected hyperbolas that we've detected. So in this case, they're probably just buried rocks in this particular case, or buried surfaces. But if you had reinforcing bar, you'd be able to see a map. Now, of course, if we wanted to, we can change our blanking radius to say, change this to 10. There we go. Okay. So this now shows a distribution of the different amplitudes across the site, only for the detected hyperbolas. So we can close out of here. We're going to go to our T-slice menu, choose the hype option, and we can just print that to the screen. And there we go, there's our map again, and we need to do our auto gainers per normal. And there we go, there's our calibrated map. Now, the depth value here obviously is not depth, it's the amplitude of the reflected signal. So this is a map that shows you the distribution of the, it shows you, it's a map that shows you the variation in the amplitude of the reflected signal, only from the hyperbolic reflectors that we detected earlier. So if you're doing this with concrete surveys where you're looking at rebar and you've detected all your rebar, what you're going to see is a map showing, for instance, areas where the rebar might be corroding faster. So it's a very useful tool for those of us doing concrete work. Okay, so if we close out of here, and if we go back to our filter menu, and we reselect filter and go search again, click on the auto search button again to redetect those same hyperbolas, just to give you a demonstration of how we can fix some errors, or we might want to manually insert some. Obviously here we've got things that are overlapping, so we can immediately say, well, I want to change the end skip value to say 100, and it will remove these ones here, for instance, that are underneath each other. However, as you can see, it's completely missed that one entirely. So yeah, you need to change. You need to decide what's the balance. You need to figure out some balance, and most concrete, I should say the rebar in concrete is, well, it's laid down in a mesh usually. What that means is that your reflectors in your radar data are going to be pretty much constant at the same depth. They're going to be more or less the same width and that sort of thing as well. So you're not going to have these issues that I'm having with this particular data set, most likely, if you're doing it correctly. This is just, I just wanted to show you how to do this with the worst possible data set so that you get a good idea as to how to deal with your own issues that you might have. And 99% of the time, if you're looking at concrete data, these issues won't be anywhere near as difficult as these are, as what I'm showing you now. So fear not if you're looking at this and thinking this is terribly difficult. It's not necessarily going to be that way for you. So let's say we want to include this hyperbola here in our system. So all we have to do, click on the insert button. There's actually instructions here. Click on the insert button, move the hyperbola, and then right click over the top of the reflector. And there we go, it's been added to the list. Now, we've created this, we've done this scan for just one line of data. What if you have a grid of, say, several hundred files? Do you want to go through each manually? No, of course not. Click on the batch search button, and it will then go through every single radargram that you've got in your dataset. In this case, we've only got 2. And there we go. It's detected every hyperbola within the dataset, which isn't many, because the second line doesn't actually have any. But and then, of course, if you wanted to, you can now go to the compile hyperbola amplitude button, and then you'll be able to create that map again. So before, what I did before was we were just looking at the map, or we were creating a map based on only 1 radargram's worth of data of reflected signals. In this case, yeah, you'd want to actually, if you're in a normal concrete scanning job, you'd want to make sure that you go on the batch search first, to be actually, so that you are getting the reflectors from throughout your entire survey area first, and then you're going to create the amplitude map. So I hope that hasn't confused you too much. Unfortunately, I don't have a very good example data set to show you with. Okay, if you have any questions, feel free to contact me. I'm available on Skype. My username is Hunter Geophysics, one word, or find me on Facebook, David Hunter. I'm in the GPR-SLICE Facebook group there. Otherwise, find me on my website, www.huntergeophysics.com. Good luck.